Stars are immense balls of gas, primarily hydrogen and helium. Deep within their cores, a cosmic dance plays out nuclear fusion. This process is the engine that powers stars, flooding the universe with light and heat. Imagine the power of countless hydrogen bombs detonating every second. That's the scale of energy production inside a star. Hydrogen atoms, under immense pressure and heat, are forced to fuse together, creating helium. This fusion releases a tremendous amount of energy, which radiates outward from the star's core. This outward pressure counteracts the inward pull of gravity, creating a delicate balance that keeps the star stable for billions of years. Think of a star like a giant pressure cooker. Gravity constantly tries to crush the star inward, while the energy released from nuclear fusion pushes outwards. This constant struggle between these two forces is what defines a star's life. This delicate balance cannot last forever. Eventually, a star exhausts the hydrogen fuel in its core. This marks the beginning of the end of a star's life, leading to a series of dramatic transformations that depend on the star's mass. When a star runs out of hydrogen in its core, the outward pressure from fusion lessens. Gravity, always present, begins to gain the upper hand. The core contracts, becoming denser and hotter. This increased temperature ignites hydrogen fusion in a shell surrounding the core, causing the star's outer layers to expand dramatically. The star balloons into a red giant, engulfing any nearby planets. For stars like our Sun, this expansion marks the end of the line. The outer layers are gradually blown away, forming a planetary nebula, a glowing cloud of gas and dust. The remaining core, now a white dwarf, cools slowly over billions of years. However, for stars significantly more massive than our Sun, the story doesn't end here. Their immense gravity drives the core to even greater temperatures and pressures, triggering further stages of nuclear fusion. Heavier elements like carbon, oxygen, and even iron are forged in the heart of these dying giants. White dwarfs are the remnants of stars similar in size to our Sun. Imagine compressing the entire mass of the Sun into an object the size of Earth. That's a white dwarf. Incredibly dense, with gravity about 100,000 times stronger than Earth's. The Chandrasekhar limit, named after the astrophysicist Subrahmanyan Chandrasekhar, defines the maximum mass a white dwarf can have, about 1.4 times the mass of our Sun. Beyond this limit, the pressure of electrons resisting further gravitational collapse is not enough, leading to a spectacular supernova explosion. White dwarfs, though incredibly hot at first, slowly cool down over billions of years. They emit no new light of their own, but continue to radiate heat as they fade into stellar embers. These stellar remnants provide valuable insights into the later stages of stellar evolution for Sun-like stars. For stars significantly more massive than our Sun, the core collapse after exhausting their nuclear fuel leads to a much more violent outcome, a supernova. The core collapses so rapidly and violently that protons and electrons are forced to combine, forming neutrons. The result is a neutron star, an object even denser than a white dwarf. Imagine squeezing the mass of two suns into a sphere only 20 kilometers across. That's the density of a neutron star, where a teaspoonful of its material would weigh billions of tons on Earth. Just like white dwarfs have a mass limit, neutron stars also have a comparable mass limit, calculated by Lev Landau. Neutron stars possess incredibly strong magnetic fields, trillions of times stronger than Earth's. These fields, combined with their rapid rotation, can accelerate particles to nearly the speed of light, creating powerful beams of radiation. These beams sweep across space like cosmic lighthouses, detectable as pulsars, flashing on and off as the beam crosses our line of sight. Section 5. Black holes. Gravity's final victory. When a star, significantly more massive than our Sun, exhausts its nuclear fuel, the core collapse is so powerful that even the resistance of neutrons is overcome. Gravity reigns supreme, crushing the core down to an infinitely small point known as a singularity. This marks the birth of a black hole, an object so dense and with such strong gravity that nothing, not even light, can escape its grasp. Imagine a waterfall, where water flows relentlessly over the edge. The closer you get to the edge, the faster the water flows, making it harder to escape its pull. Eventually, you reach a point of no return, where even the fastest swimmer can't fight the current. This point of no return around a black hole is called the event horizon. Once you cross it, there's no turning back. You're destined to fall into the singularity, where all matter is thought to be compressed into an infinitely small point. Section 6. The point of no return, singularity and the event horizon. The singularity at the heart of a black hole is a point of infinite density and zero volume, where the laws of physics as we know them break down. We don't yet have a complete theory of gravity that can describe what happens at the singularity. It's a realm where our current understanding of space, time and matter is insufficient. The event horizon, however, is a boundary in space-time beyond which events cannot affect an outside observer. It's like a one-way membrane. Information can enter the black hole, but nothing, not even light, can escape from within the event horizon. Think of the event horizon as the point of no return for a waterfall. Once you cross it, the pull of gravity is so strong that you're destined to fall into the singularity, regardless of how hard you fight against it. Section 7. Cosmic censorship hiding the singularity. The singularity at the heart of a black hole presents a challenge to our understanding of physics. Its infinite density and zero volume suggest a breakdown of our current theories. However, there's a hypothesis called the cosmic censorship conjecture that suggests that singularities, these points of ultimate breakdown, are always hidden from the rest of the universe by event horizons. This conjecture implies that the universe has a way of hiding these points of extreme physics from us, preventing us from directly observing them. Whether this conjecture holds true is still a matter of debate and active research. If the cosmic censorship conjecture is correct, then the singularity at the heart of a black hole remains forever shrouded from our view, hidden behind the veil of the event horizon. Section 8. Falling into a black hole. A one-way trip. Imagine falling into a black hole. As you approach the event horizon, you wouldn't notice anything particularly dramatic. However, from an outside observer's perspective, you would appear to slow down, your image becoming increasingly redshifted as your light struggles to escape the black hole's gravitational pull. Once you cross the event horizon, there's no turning back. You would continue to fall towards the singularity, experiencing the effects of spaghettification along the way. This is the stretching and compressing effect of the immense tidal forces near a black hole, stretching you like spaghetti as you fall towards the singularity. The journey into a black hole is a one-way trip. Once you cross the event horizon, you're destined to meet your fate at the singularity, where our current understanding of physics breaks down. Section 9. Black holes' windows to the universe. Black holes, though once considered purely theoretical objects, are now recognized as fundamental components of our universe. They play a crucial role in the evolution of galaxies, influencing star formation and shaping the distribution of matter. By studying black holes, we gain insights into the extreme limits of gravity, the nature of space-time, and the ultimate fate of matter. They serve as cosmic laboratories, allowing us to test our understanding of physics under the most extreme conditions. The study of black holes continues to push the boundaries of our knowledge, revealing the intricate workings of our universe and challenging us to expand our understanding of the cosmos. Section 10. The enduring mystery. Black holes remain some of the most mysterious objects in the universe. While we have made significant strides in understanding their properties and behavior, many questions remain unanswered. What happens at the singularity? Does the cosmic censorship conjecture hold true? How do black holes influence the evolution of the universe? These questions continue to drive scientific inquiry, inspiring new theories and pushing the boundaries of our knowledge. The study of black holes is a journey into the unknown, a quest to unravel the deepest mysteries of the cosmos. The universe is full of wonders, and black holes stand as a testament to the power of gravity, and the enduring mystery that surrounds these cosmic giants. Their study will continue to captivate our imagination and inspire us to explore the cosmos for generations to come.